Thank you very much for attending this session. Today I'm going to have a little bit additional example and talk about a little bit other thing related to throughput and capacity. Let's first solve problem. We have already solved similar problems, very similar problems. Let's just repeat one additional example. So we have three resource pools indeed. Resource pool 1 has 4 resources. Unit load of each one is 20 divided by 3. I have put 20 divided by 3 because I didn't want to put 6.666666667. In 20 hours, this station can produce 3 products for each of its resources. There are 4 resources in this resource pool. Capacity of each one of these resources is RP1, for example, equal to 1 divided by TP, and that is 1 divided by 20 divided by 3, which is equal to 3 divided by 20. 3 divided by 20 units per what? Per hour, because this 20 was hour. So this is 3 divided by 20 products per hour. But we have 4 of these resources, so the capacity of the resource pool is equal to 4 times 3 divided by 20, which is 12 divided by 20, or it is 0.6. This is the capacity of this resource pool. Per watt, still per hour, 0.6 per hour. And if we are working for 8 hours, that would be 8 multiplied by 0.6, that is 4.8 units of product or flow units per day. That is the capacity of the first station. From the start, we could have said RP is equal to C divided by TP. C, the number of resource units in that specific resource pool, which, as we see here, it is 4. Divided by TP. TP is 20 divided by 3. So that is 20 divided by 3. And that is equal to 12 divided by 20 units per hour. That is capacity of this station. Now you can continue for the next 2 stations exactly in the same procedure. Station 1 has 4.8 capacity, station 2 capacity of 12, and station 3 capacity of 8. And the problem says throughput is equal to 3.6. So throughput for all of them is 3.6. These are utilization. So we have utilization of all resources. And we want to know how many flow units are in each resource pool. Utilization of the first station is 0.75. What this 0.75 means? It means each resource is with a flow unit for 75% of time and is idle for 25% of time. But we have 4 of these resources. 4. Therefore, the number of flow units which are in this resource pool are 4 multiplied by 0.75. Utilization of the second station is 0.3. That means that the station for 30% of time is with a flow unit, and for 70% of time is idle. Therefore, on average, it is with 0.3 times 3, which is 0.9 flow units. And this one is 0.45. 2 times 0.45, that is also 0.9. So these are flow units with each station, and when we add them up, on average, 4.8 flow units are inside this system. That was the first way of computing it using utilization. But there is also another way to compute it. I would like you to spend a minute to see how can we compute it from a different way. And that different way is by using the Liddell's law. This one by using utilization. The second way is by using the Liddell's law. Okay, using the Liddell's law, throughput, the problem is stating that it is equal to 3.6. Through the Liddell's law, I know throughput times flow time is equal to inventory. And we are looking for inventory with these resource pools. Throughput I have, if I can find flow time, and this is what we call it theoretical flow time, because it only takes into account the time that the flow unit spends with resources. Later on, we will talk about flow time, which is the time that the flow unit spends with the processor resources, plus the time that it spends in the waiting lines. That is flow time. Time in waiting line and time in processors. The time that they spend in processor, we refer to it as the theoretical flow time, and the unit load is different pieces of it. Okay, let's see how much time each flow unit spends with each of these resources. When a flow unit comes in, it goes to station 1, and the time that it spends over there is 20 divided by 3. No matter if I have 1 resource unit or 100 resource unit, when a flow unit comes in, when an application comes in, it should go into one of them and stay for 20 divided by 3 hours. 6.666667 hours. That is the time that each and every flow unit spends with a processor. So I have 20 divided by 3. Here, 2 hours plus 2 hours. And here again, 2 hours. No matter if there are 1 resource unit or 100 resource unit in each of those resource pools, each flow unit which comes in, each application which comes in, should spend 2 hours here and 2 hours here. So that is 2 plus 2. And if this is 6.667 plus 2 is equal to 10.667. That is flow time, or indeed, as I explained, theoretical flow time. Now I have flow time, I put it over there. I have throughput, I put it over there, and I will get inventory. That is, throughput is 3.6 per day. Flow time is 10.667 hours. This is day, this is hour. I cannot multiply these two by each other. I either should divide 3.6 by 8 to make it per hour, or divide 10.667 divided by 8 to make this one per day. Either 3.6 divided by 8 to make it throughput per hour, or 10.667 divided by 8 to make it in terms of day. Both of them are fine. 10.667, 3.6, when we do the computation, we get the same 4.8. Suppose there are 16.8 flow units also inside the waiting lines, in front of station 1, station 2, station 3, or even after station 3. These are inventory applicants, flow units in the waiting lines in different stage of this process. 16.8. Compute the flow time. Each process is composed of two parts. A value-added part, which is the process, and a non-value-added part, which is the waiting line. They are always there. No matter how much capacity do we have, due to variability, we always have a waiting line. And now we want to know how long does it take for a flow unit to come from this point and go to this point. We know that number of flow units that are with the processors are 4.8, and this one state that 16.8 are also waiting here. The answer is quite simple. Throughput is equal to 3.6 per day. I is equal to 16.8 plus 4.8, which is equal to 21.6, and therefore throughput times flow time is equal to inventory. 3.6 times flow time is equal to 21.6, and flow time is 21.6 divided by 3.6, which is 6. But 6 what? 6 days. Why days? Because throughput was in terms of days. We have an inventory of 21.6 inside this process. We throw it out, we process it and send it out. Do not throw it out. We process it and send it out to the market or to the applicants at rate of 3.6 per day. And when we divide these two by each other, the flow time that we get is in terms of days. If you want it in terms of hours, just multiply by 8, because a day is 8 hours. Let me take this opportunity and explain two things. One is cycle time, and the other one is takt time. Cycle time is how often we can send a product out. Let's look at this system. Capacity of this system is equal to capacity of its bottleneck, which is 4.8. That is equal to RP, throughput. And if you remember, per hour it was 0.6. 0.6 per hour. 1 hour, I can produce 0.6 product units. How long do I need to produce 1 unit? It's equal to 1 multiplied by 1 divided by 0.6. And therefore that is 1 divided by 0.6. Therefore, cycle time is equal to 1 divided by RP. And then depending on RP is stated in what terms: hour, minute, second, day, week, months, whatever. Cycle time will be also stated in the same term. In this situation, RP was defined per hour. Therefore, cycle time would be hours. 1 divided by 0.6 hours. 1.666667, that is cycle time. Every 1.666667 hours, we can produce one product. We can produce one product in this time period. Takt time is defined as 1 divided by throughput. Cycle time, 1 divided by capacity. Takt time, 1 divided by throughput. Day. In 1 day, I need to produce. That is what the market asks me. Cycle time goes to production capabilities. Takt time goes to demand requirements. In 1 day, market asks me to produce 3.6 product. Market in 1 day expects me to send out 3.6 products. How often market expect me to send 1 product? How often the market expect me to send 1 product? And that is equal to 1 multiplied by 1 divided by 3.6 days. If I multiply it by 8, it will be hours. Always takt time is bigger than cycle time, because cycle time tells me how often I can send the product out. Takt time tells me market expect you how often to send the product out. And I cannot send product out in the period which is shorter than my cycle time. Capacity is always greater than throughput. Cycle time is always less than takt time. Capacity is always greater than throughput. Then 1 divided by capacity is cycle time, 1 divided by throughput is takt time. Takt time is always larger than cycle time, because market give me more time to send the product out. If it gets me less time, then I should go above 100% utilization. I cannot go above 100% utilization, and therefore I need to increase my capacity. Here, in this specific example, takt time is equal to 1 divided by 3.6. That is this many days. If I multiply this by 8, then that is takt. Can the company handle 150 cases per month? A month is 20 days in this problem. So if we divide that, it would be 7.5. If the market expects us to send out 7.5, unfortunately, we only have capacity of 4.8 per day. We know that utilization is equal to throughput divided by capacity. If we divide these two by each other, we get a number greater than 1. Whenever this number comes out greater than 1, we don't refer to it as utilization. We refer to it as implied utilization. Implied utilization. And that means we need to think about ways to increase capacity. Don't forget, capacity is C, which is the number of resources, divided by TP. If you want to increase this, we either need to increase the numerator or decrease the denominator. These are the only possible ways. Capacity of a single unit in the first station is 1.2. Why it is 1.2? Because Each unit requires 20 divided by 3 hours, and therefore RP of a single resource is 3 divided by 20, which is equal to 0.15 per hour. And then a day is 8 hours. Therefore, if you multiply these two by each other, that is the capacity per day. We need 7.5 per day. Capacity of each resource unit in the second resource is 4, so we need 1.87. And capacity of each resource unit in the third station is 4. Therefore, we have these numbers. We need 6.25 in station 1, 1.87 in station 2, and 1.875 in station 3. Or indeed, we need 7, 2, and 2. We have 4 and 3 and 2. Therefore, in station 2, we have more than what we need. But in station 1, we are 3 resource units short. We may hire 3 additional paralegals. Or we may just hire 2 and have 6 paralegals. We will be short for 0.25 paralegals. 0.25 times 8 would be 2 hours per day. We have 6 paralegals. We may ask them, all 6 of them, to work 2 hours extra time, overtime per each paralegal. Or alternatively, we may ask the resource 2 to help resource 1. And instead of asking for overtime, we may have a help from resource 2 to meet the requirement. This is a very important task. Let me give you an example. Suppose we have 2 resources. The first resource is very expert in his or her own work. He can complete each incoming flow units in 5 minutes. So TP is quite short. Capacity is 12 per hour. The second resource is also expert in its own job. It can handle the job in 10 minutes. It's a different job, a little bit more, not a little bit, more complicated job. So the capacity of the second resource is 6 per hour. We have 2 resources. They both work excellent. They are perfect in their own job, and capacity of the system is 6 per hour because capacity of the bottleneck is 6 per hour. Now suppose we cross-train these 2 people to be able to do each other's job. So the first resource here in this situation, suppose, can handle the second job too, but it will not be as effective as before, even it's its own job, because it should go back and forth to the second job and come back. Suppose instead of 5 minutes, now this resource can do its task in 6 minutes instead of 5 minutes, and can handle the task of the second resource not in 10 minutes but in 12 minutes. So under the new situation, he can complete 7 units in the first task, and that will take 42 minutes, and still has 18 minutes for the second task, where he can complete 1.5 tasks because he can do that task in 12 minutes. Or he can just enjoy 6 minute relaxed time. Here I also need to mention a very important feature in management of systems. Performance of each subsystem should be gauged to the performance of the total system. Here, it doesn't matter if this resource can produce 12 products per hour because capacity of the system is 6 per hour. However, if we make him to produce 7 units per hour and do 1 unit in the next station, capacity will go from 6 up to 7. That is what I mean by performance of all subsystems should be linked to the performance of the total system. Here, in the second situation, the first operator produces less product, but because production of the total system moves up from 6 to 7, he's doing better, or she's doing better.